In this video, I'm going to be explaining how to find higher order derivatives. So we can start with two different notations. I could describe a function using f of x, and then when I derive it, I put an apostrophe next to the f. That's the first order derivative or the first derivative. If I derive the derivative, I get the second order derivative or the second derivative, and I just add an apostrophe each time I find its derivative. We can do that until we run out of differentiable functions. So if I get to a constant number, I can't find its derivative, and that would be the end of the derivative line. We can do it with different notation. If I use y instead of f of x, then its derivative would be dy over dx. And if I derived that function, I would get the second order derivative. So we just increase the degrees or the orders by adding more numbers or a higher order or degree. Let's do some examples where we find second order derivatives. So given the original function x cubed minus x squared, I could use my power rule to find the first derivative and get 3x squared minus 2x, and then use my power rule again to derive the first derivative and get my second derivative, which is 6x minus 2. I could find a third derivative of this, but that would be as far as I could go. Let's find zeros of the second derivative. We can set our second derivative equal to 0, and we could factor to find the zeros and find a solution as 1/3. Let's do another example, a little bit more complicated function, the square root of the quantity 1 plus 2x. The first thing I would want to do is rewrite that radical as a fractional exponent. So a square root is the same as raising it to the power of 1/2. Then I could use my power rule and my chain rule combined to find the first derivative, and then simplify and get our first derivative. Then derive that one more time, and I could find the second derivative. So again, I would have to use my power rule and my chain rule combined, and I could simplify and find my second derivative. Sometimes we could find zeros of the second derivative. Other times we could find values at which our second derivative is undefined. So this would be an example where we don't have any zeros, but we do have values where it's undefined. So I could find the zeros in this form, or I could rewrite it and visualize it a little better by flipping my function because of the negative exponent and rewriting it back into radical form. Then I could visualize that if the bottom here, if the denominator was 0, my function would be undefined. So if I could get the square root to 0, then the denominator would be 0. So anything under the square root, if that's 0, then the square root is 0. So I know that 1 plus 2x, if that's 0, then the whole thing is 0. So find the zeros of just 1 plus 2x, and we get x equals negative 1/2. So if I plug negative 1/2 in, I would get an undefined value of this function. One more example, let's do a trig function. Let's find the first derivative, just using the chain rule, and simplifying. Then derive that to find the second derivative, again using the chain rule and simplifying. And we get our second derivative. So we can find zeros as long as we state a domain on which we're finding them. So zeros of the second derivative, we can divide both sides by 12 and just find zeros of sine of 2x. And actually we could imagine that we're just finding zeros of sine of x first, and then work with that. So zeros of a sine function on this domain are going to be positive and negative pi and 0, places where our height is 0. And then we could solve for the 2x. So I know that I want 2x to equal positive or negative pi or 0. So I'm going to just solve those equations. If 2x is 0, then x has to be 0. So if I plug 0 in, 2 times 0 is 0, and sine of 0 is 0. If I know that I want 2x to equal negative pi, well, I can divide both sides by 2. And I know that if I plug in negative pi over 2, then 2 times negative pi over 2 is negative pi, and the sine of that is 0. And I can do the same thing with positive pi and plug in pi over 2, and that would simplify to just pi, and the sine of pi is 0. So the solutions, or the zeros, of my second derivative are positive and negative pi over 2 and 0. So there's an introduction to higher order derivatives. As long as you can derive it, you can find higher order derivatives.